Hello everyone. So here we have a AP Chemistry free response, and now the AP exam is about less than 3 months from now. You want to get this started. So today I'm just gonna go over question 1. A lot of points are in the first 3 questions. As you can see in the direction, question 1 through 3 are long free response questions, and you should spend about 23 minutes to answer. And they're worth 10 points each. That's a lot. Okay, you get 30 points from the first 3, and if you skip any of these, it can be detrimental to your score. Now, question 4 through 7 are short ones, and you should be able to finish quickly, relatively quickly, and they're only 4 points each. So 4, 5, 6, 7, 7 times 4, 5, 6, 7, 4 questions, 4 times 4 only give you 16. Alright, so number 1, we have acid and base chemical reactions. So it said the student is studying the reaction between the lactic acid, C3H6O3, and NaOH, the strong base, the sodium hydroxide NaOH, as represented by the balance equations above. Now, the moment you see the question, you notice that this is not one of the 6 strong acids. So we have a weak acid here, and then we have strong base. So we should expect some buffer to show up, and we'll have a conjugate base here and the conjugate acid. So part A is asking us, is telling us that structural formula for lactic acid is shown in the following diagram. Circle the hydrogen atom that most readily participate in the chemical reaction with the sodium hydroxide. Now, sodium hydroxide is a very strong base. In water, it will fully dissociate into OH minus, and it can protonate one of the hydrogen here. Now, not the methyl one, okay? That's not where the acid and base reaction occur. So you can totally ignore these 4 on the left. But between these two, there's an inductive effect that if you have 2 oxygen being very electronegative, they will pull the electron away from the hydrogen. So this hydrogen is kind of like barely hanging on to it, because these 2 electrons are pulling the electron toward themselves. Again, the electron between O and H is really weak. So you have to answer that this one, the hydrogen on the right, is most readily participates. Okay, you have to circle this one. Again, that's because of the inductive effect of the nature of oxygen being electronegatives, and there's 2 of them versus just 1 here. Alright, so I don't think they ask you to justify it, so you just have to circle that one. And part B, the student begins the experiment by dissolving 10.22 grams of sodium hydroxide, and they give the molar mass, that's quite nice, in enough water to produce a 500 milliliter of solution, and calculate the molarity of the sodium hydroxide in the solution. So goal is concentration, okay, molarity of sodium hydroxide. Okay, let's start with the given. We have 10.22 grams of sodium hydroxide, and they give you the molar mass. The least thing you can do is by the mole. Okay, if you are very not savvy in chemistry and you had a very bad school AP Chem teacher, at least you should know how to convert the grams to mole. Okay, simply put, you need the gram on the bottom here, so that the grams of sodium hydroxide can cancel, and we have 1 mole of sodium hydroxide. Remember, the concentration is always measured in moles per liter. So we got the mole part done, but we also gotta get the volume part. Okay, so the volume is 500 milliliter, but if it's mole per liter, we gotta convert the 500 milliliter into liter. So 1000 milliliter equals 1 liter. The milliliter cancel. We get the mole of sodium hydroxide per liter of solution. And you know that 500 over 1000 give you 1/2. So we have 1/2 here. Okay, we'll just use calculator. On AP exam, they will let you use graphing calculator as well as the scientific calculator. I say just get the graphing one. Okay, and divide it by 0.5, and you're gonna get 0.511. Okay, make sure you show your work. And your answer should be 0.511 molarity of NaOH, sodium hydroxide. Okay, next one. You know what? Let me get onto Zoom so I can annotate. Alright, so I got into Zoom so I can annotate here because I will have to grab this. Okay, the student uses a sodium hydroxide solution from part B, a burette pH meter, and 100 milliliter of Erlenmeyer flask to titrate 25 milliliter of sample of lactic acid solution. The student data are shown in the following graph. So you guys should be able to tell where the equivalence point is and where the half equivalence, or so-called the best buffer region. Now buffer region will be all here, but the best one will be the half equivalence. And equivalence point is where stoichiometrically you have a number of acid and number of base equal to each other. And that's when there is a sudden spike in your pH number. Okay, so at 16 millimeter, keep that in mind that we have an equivalence point. Again, that's when the concentration of our moles of OH minus is equal to moles of the lactic acid, C3H6O. Let me double check. Oh, I forgot another 3 here. Okay. Okay. Alright, so but we have to find out the pKa of the lactic acid. Okay, so if you want to find the pKa, the good information we can pull out is a Henderson Hasselbalch equation. So pH equals pKa plus log of the conjugate base, which should be a C3H6O. Let me double check. Yeah, C3H5O3 minus over the acid C3H6O3. So to determine the pKa, pKa will be equal to pH when we have a half equivalence point. So at half equivalence point, the ratio of the concentration of the conjugate base and acid will be equal. Okay, so at half equivalence point, these two will be equal. So when you have a same ratio, it will make it 1, and log of 1 just goes 0. Again, log of 1 is equal to 0. Okay, so now that we know it, we know the equivalence point is 16 millimeter. That half equivalence point is at 8 millimeter of sodium hydroxide that got used. So right here, this is a half equivalence point. And if you go to the right, at 8 milliliter of sodium hydroxide that got used up, and just go straight to the left. Alright, it's really hard to tell, but you kind of have to make an assumption. And anything like, I know that my line has to be more toward 4. I'm just going to use 3.8. Okay. And I'm pretty sure they have some range that they tolerate. So make sure you try your best to approximate it. So I'm gonna say pKa of 3.8. Now part D, the preceding diagram, here we have a diagram, represents the relative amount of major species in the sample of solution in the flask at one point during the titration. Note that water molecules are omitted. Okay, draw an X in the preceding titration curve at a point in the titration where the reaction mixture would be represented by this diagram. And then we need to justify the answer. Alright, so if you look at the ratio of C3, let's just write, I'm gonna write down the major reaction, and then we'll compare it. Okay, we have 4 moles or 4 molecule of C3H, the lactic acid. I'm not seeing any OH minus, but I do see 2 hydroxide here. Okay, 2 molecules of hydroxide. And then I do see the 2 conjugate base of lactic acid. So 2 molecule, we can just say mole, just for simplicity. 2 moles of the conjugate base. And water, we can omit it. From this, we can deduce that we can just assume that because we still have 2 moles of the lactic base, but we have more of the lactic acid. So in other words, we have a 2-to-1 ratio of acid and conjugate base. Now recall that they have to be same ratio, 2-to-2 ratio. Like if it's a 3 of this diagram, 3 of the white circle with a big circle, and then 3 of the this, then we will be in the exact what is it called, the half equivalence point. But we are not. Remember, we're adding the strong base continuously, and we start with more acid. That's why the pH is low, and that means we haven't got there yet. If you know that the equivalence point is 16, that's when you run out of the acid because of continuous inflow of the strong base sodium hydroxide. We haven't got there yet, not even close. So we didn't run out of all the acid, but instead we have more. It's not even 1-on-1 ratio. So we have to have something less than 8 here. Okay. So one way is that if you know that to run out an entire 16 milliliter of strong base, if you got only 1/3 done, in other words, you start with all the acid and you only convert to 1 out of 3, you can do the ratio that 16/3 is going to give you about 5.3 milliliter of sodium hydroxide. Okay, so if you put your X on like as close as possible to 5.3, okay, so this is 5 here, so right there they'll be perfect. Okay, based on the ratio of this acid and conjugate base. Now what's another way? Another way is that you can use a Henderson-Hasselbalch equation. Assuming I use the 3.8 from part C as my pKa. Okay, let's recall that again. pH equals pKa plus log of the conjugate base. Conjugate base, what is it? C3H5O3 minus, and okay, assuming you use this, I use the 3.8. And I'm gonna say that the ratio is the acid on the bottom is bigger than the conjugate base here. So I'm gonna put 2 to 1 like that. Then 3.8 plus log 0.5 is gonna give you like 3.5. So if you look at the graph here, and then you know that this is 3 pH, and if you go straight to the right, 3.5, you know, we're gonna get around the same place again, and you can just surmise from there. So there are 2 ways you can do this. Okay, so yeah, approximately 5.3 millimeter, somewhere between 5 and 6 will be a good answer choices. Alright, so that's how you answer it 1. And answer 2, you can either show the equation like in Henderson Hasselbalch equation, or you can just use that equivalence point. Is the point where you run out of the acid, and if you still have a 2 to 1 ratio from the 16 millimeter span, you know, you just get the 1/3. You're like a 1/3 way in to convert the acid to base, and you can talk about 5.3 milliliter of NaOH just got used to get this ratio. All right, moving on. Now we got the student response experiment that uses a solution of sodium hydroxide with twice the concentration as shown in the preceding table. On the following graph, draw the titration curve that would be expected for experiment 2. Alright, so if you look at the first one that has a 10.22 gram, we are telling you the experiment 1 is the same graph we just saw earlier. But instead, we're gonna put more mass given the same volume. So what happened to our concentration? It doubles. So if you put the same amount of NaOH, volume might be same, but we put more moles of NaOH, therefore it's going to be faster, or it will pull your equivalence point half as much. So you're just gonna have to grab or move your equivalence point to 8 instead of 16, and then you just connect them. Alright, it's kind of hard to draw with my mouse, but should look something like that. Okay, that's because again, you have more moles in the same volume that's going to combine with the acid, and the more moles of NaOH, the faster you will reach the equivalence point. So it's proportional. Alright, and then part E, and let me erase this. Part E, in the third experiment, the student investigates the enthalpy of the reaction between the lactic acid and sodium hydroxide. The student combines 100 milliliter of a 0.5 molar lactic acid solution at 20 degrees with 100 milliliter of a 0.5 molar NaOH solution at 20 Celsius in calorimeter. The final temperature of the resulting combined solution is 23.2 Celsius. Assume that the density of each solution before combining is 1 gram per milliliter, like typical aqueous solution, and that specific heat capacity of combined solution is 4.2 joule per gram per Celsius. Calculate the quantity of heat produced in the reaction. So the goal is to find the quantity of heat. Now in chemistry, that symbol is Q. Okay, we need to find Q here. Q equals mc delta T. Okay, but the student combined 100 milliliter, 100 milliliter. So we have a 200 milliliter of volume. And if you multiply that with the density of the solution, Per milliliter, you get 1.0 gram. You're gonna get 200, and we have a 3 stick pick, 200 grams of 200 grams of the solution, or NaOH solution. And then the specific of capacity is given 4.2 joule per gram per Celsius. Now, as far as the temperature goes, this delta represents the final minus initial. So final temperature minus initial temperature is, they told us that 23.2 is the final. And the initial, you start with the 20 degrees for each solution, lactic acid and the sodium hydroxide, 20. And you get 3.2 Celsius. Now for stick pick, when you have a 10th place and 10th place, I will keep the 10th place. So I have 2 stick pick here, 2 stick pick, and 3 stick pick. So my overall stick pick for Q has to be 2 stick pick. So now I multiply all these values. Now, it's also good practice if you have time to check your units or cancel. And in my case, it does. Okay, Celsius cancel, grams cancel. So 200 times 4.2 times 3.2 gives you 2,688 joule. But like I said, we have a 2 stick pick, 2 stick pick, and 3 stick pick. You want to show that I should 2 stick pick joule. They also told us that write the answer in joule, so do not convert it into kilojoule. Now, can you write this scientific notation? Absolutely. You can also say 2.7 times 10 to the power of third joule, so both are acceptable. Now, for part 2 of number 1, E. So this is still E. Roman numeral 2 now. Calculate the molar enthalpy of the reaction in kilojoule per mole of reaction and include a sign in your answer. So be careful. If you have minus or plus, it matters here. So you have to think it this way. This calorimeter is the measuring device where you put the temperature thermometer in it to measure the temperature. And it's the chemical that our focus is in. The water being surrounding got higher because the temperature received 3.2 degrees, it got higher. So that means the chemical reaction is actually minus. So because the Q solution is plus because the temperature increased, the Q reaction on the other hand has to lose the energy. So because of that, we're gonna need to put, okay, so let me start with the formula. The enthalpy of reaction has to be Q of reaction over the N of the reaction, the moles of reactions. So Q of reaction should be negative 2700 joule per how many moles? Now thing is, both are the limiting reactant. In other words, we have a 1-to-1 mole ratio in our main reaction. Not only that, we end up using 100 milliliter of 0.5 molar and 100 milliliter of 0.5 molar with a 1-to-1 ratio. They are to be consumed completely. So we can just use, let's see, let's just find the moles of reaction as 0.10 liter times 0.50 moles per liter. The liters cancel. And they also want us to write this in kilojoule. Okay, so this is moles of reaction. And we gotta multiply 1 kilojoule on the top and 1000 joule on the bottom and cancel out the joule. Okay, we get the kilojoule per moles of reaction, and let's just put this all in our calculator. 2700 divided by 1000 and then divided by 0.1, and divided by 0.5 gives us 54. But there's a minus here, so it's minus 54 kilojoule per mole of reaction. Okay, so that's how you answer the part 2. And part 3. Alright, so this is the last one. The student claims that if heat is lost from the calorimeter to the surrounding air during the reaction, then the experiment values for the molar enthalpy of reaction will be smaller in magnitude than the actual value. Do you agree or disagree with him or her? Justify your answer. Okay, so when you do experiments, some things are bound to lose. So if the heat is lost in the calorimeter, then the temperature change will be less varying. So let's go back to our formula, Q equals mc delta T. And if you look at that Q and delta T, they are proportional to each other. So if you lost the heat by accident, your Q value will also decrease by proportion. Okay, so you're gonna agree, yes. You agree, and we're gonna just describe that. Okay, they want to justify our answer. We agree because when there is loss of heat from the calorimeter, the T, delta T being proportional to Q will reflect lower heat evolved from the reaction. Therefore, the molar enthalpy of reaction will be smaller. We saw earlier already that delta H equals Q of reaction over N of mole. The moles doesn't change, the number of mole doesn't change, but the Q will be lower. Okay, when Q will be lower because of the temperature change being less, then molar heat capacity by proportion should also decrease, and that's somewhere along the line you have to describe that way. Okay, so I hope this helped you guys, and good luck on your study of AP Chem. I'll continue to make number 2 probably tomorrow, but not guaranteed. Either way, thank you very much, and if you like my video, please subscribe